So far in Chapter 9, you've learned about transformations such as reflections and translations. The next transformation is called a rotation. A rotation is turning a geometric figure around a point. Things to know about a rotation is that it's an isometry. It's a rigid motion that preserves the side lengths and the angle widths of every part of your shape. So your end result, your image, is congruent to your pre-image. The second thing to know about rotations is that they're almost always counterclockwise. So for this example here, when you're asked to rotate this pre-image 82 degrees, it means 82 degrees counterclockwise. Now, if you ever have a negative degree rotation, that would be clockwise. A pinwheel is a really good analogy for rotations. The idea that you can have a shape like this that rotates around that center point. The shape of that part of the pinwheel doesn't change as it rotates, but the direction it faces will. Question 1. What is the measure in degrees of the angle of rotation about point O that maps or moves point N to point L? So a good starting place with rotation problems is to figure out how many degrees wide each section of your diagram is. So you know this full circle is 360 degrees, and there's 4 congruent sections to that circle around point O. So you could say each of those sections is 90 degrees wide. 360 divided by 4 is 90 degrees. Now, if we're mapping point N to point L, remember that with rotations, we're moving counterclockwise. So it would be going from here to here in that direction. That would be 1, 2, 3 of those 90-degree jumps. 90 times 3, that'd be a 270-degree rotation. Pause here and try part B. You should get its 2 jumps of 90 degrees, so a 180-degree rotation. Point N is the center of the regular hexagon given here. What is the image, or the result, of the given point or segment for the given rotation? So what is the image of a 60-degree rotation of point X about or around point N? So this about N is really just means that N is the center point. It's the pin in the pinwheel and everything else is spinning around it. So we're rotating X 60 degrees. Like the last problem, a good starting point is to figure out how wide each section in that circle around point N is. There's 6 sections, so the 360-degree circle split 6 ways, 60 degrees. So you really only need to get 60 degrees away from point X is you just need to make one jump in a counterclockwise direction. So the image or the result would be A. Pause here and try B and C on your own. For B, if each section is a 60-degree jump from the previous, to go 120 degrees, that would be 2 jumps counterclockwise. If you're starting at H and going 2 jumps counterclockwise, you would end up at X. Now, this last one's a bit of a challenge question. It's a 180-degree rotation, so that would be, if each jump is 60 degrees, that'd be 3 jumps. But the thing about it is you're rotating the whole segment HE. So we're rotating the HE segment 3 jumps counterclockwise. 1, 2, 3. So the segment it ends up on is segment AG. Pause here and try all of question 3 on your own. Go ahead and check your answers. Now, sometimes you are not given a diagram to work from, just a description. Like number 4, what is the measure of the angle of rotation for the regular octagon, given here, that maps point F onto point K? So if the name of the octagon is DEFGHIJK, the order tells you a little bit about how far apart F and Q are in terms of degrees. Well, we'll get to that in a minute. First off, you know that it's a regular octagon, so you know that the 360 circle around the center point is split into 8 sections. So each section is 45 degrees apart. For example, D would be 45 degrees away from E, E would be 45 degrees away from F, and so on. So to figure out what degree rotation would map F onto K, you can look at the name and figure out how far apart F and K are. Going from F to K is 5 jumps. So if each jump is 45 degrees, that's 45 times 5, 225 degrees total. If you really wanted to, you could draw the octagon, but you don't really need to. Unless you're a very visual learner, you could probably get away with just looking at the name of the shape. Rotations on a coordinate plane. Now, there's a list here on your paper of really helpful shortcuts to rotate things on a graph. So a good rule of thumb is a rotation of 90 degrees about the origin. Really just takes the original point, switches the order, and makes what used to be y negative. And then each common degree rotation has its own rule. A quick note about the notation for this. You want to use lowercase r's when you're talking about rotations because we're already using uppercase r's for reflections. And what you tend to see in the subscript, a little bit lower than the r itself, is a degree rotation, comma, and then the point around which you are rotating. We call the center of your graph the origin. This O is just the abbreviation for origin. So number 5, find the coordinates of the image, then graph it. So here we want to find the image of A after it's rotated 90 degrees about the origin. So that's 90 degrees counterclockwise because rotations that are positive are always counterclockwise. So first off, let's figure out where A is. A is at 4, 2. In that point, the x value is 4, the y value is 2. So if we want to figure out what the 90-degree rotation of that is, we're following this first rule. So if y was 2, that would go first and become negative, and if x was 4, that would be second. So negative 2, 4, that's our result. That's our image after the 90-degree rotation. Now, what I want you to do now is I want you to use a ruler to draw a line connecting your negative 2, 4 to your origin, and also use your ruler to draw a line connecting your original pre-image point to the origin. Do that, and you're going to notice that it does look like a 90-degree rotation about the origin. Pause here and try 6 and 7 on your own. For 6, you should get negative 4, negative 2. And when you graph that and connect that to the origin as well as the original, it should look like a 180-degree rotation. For 7, you should get 2, negative 4. 270 degrees is really just 3 times 90, so it's 3/4 of a circle essentially. And if you connect it here, it does look like it's making 3/4 of a circle spin around the origin. Great job today, everybody. Don't forget to turn in a picture of your notes on Schoology when you're done.